So why do we refer to the structure as abstract syntax tree? Well, of course, syntax, because it encapsulates the logic of the arithmetic operators. Tree, of course, because it's a tree. But why is it called abstract? And the reason that we refer to it as abstract, because, for example, our input could look like this. So this same input, maybe we could say open 1 plus 2, close, multiply 6. Okay, maybe we could use some kind of different language to represent this logic, this expression. This idea of arithmetic expression could be presented to the program in a completely different way. Right? It could be verbally generated by conversion from voice to text and then to something like this, and then also be processed. So this input and this input, both of these represent the same idea. So abstract syntax tree is abstracting itself away from the specific input language, grammar rules, whatever was used to specify this expression. So it effectively represents the logical structure of our arithmetic expression. And so this is no longer tied to any sort of, parentheses or whatever we use to specify the entire expression. So that's why it's called abstract. All right, so the next set of ideas is going to be focusing on the lexer class. So we're going to continue discussing the internal organization of the lexer class. And for this, we need to talk about grammar. So in order to be able to determine whether we have a good input or input that should result in an error, we are going to apply these formal grammar rules. So we begin with this sort of pseudocode, declarative specification of all the rules that the lexer is supposed to implement. So let's begin and say that to understand the input, the lexer class uses the following grammar rules. So these are just a formally written set of rules, and let's just examine them, part by part. What is the meaning of rules? And the rules are actually written with this highlight right here: expression, term, and primary. So what is the meaning of rules? Well, we say that arithmetic expression right here starts with the term and ends with the term. So we essentially, it needs to determine that something that was given to us as an input can be understood as a term. I believe I have a copy of these grammar rules at the bottom of our source file right here, so we can refer to this to the same definition as we move along our handout. Okay, so let's continue, and we just said that the expression begins with the term and ends with the term. The next part here says that what is the term? The term begins with definition of primary and ends with definition of primary. And then what is primary? So the primary essentially is defined as a number, the negative sign followed by the number, positive sign followed by the number, and another expression enclosed in parentheses. In addition to this, in the future, we can use assignment here and say that some kind of variable name can be followed by the assignment operator and the expression that follows, that everything here defined at the top starts here again, and so we can implement the assignment this way. So this is the idea of the primary rule. And of course, you can see that all comes down here to term being defined as primary, and then the primary is defined as a number, minus number, plus number, or parentheses that enclose another construct that starts right at the top and again follows all these rules. So in the future, the primary can accommodate a grammar for assignment, as I mentioned. And although these rules are highly abstract and not written in Java, the corresponding methods in a lecture class do have expression rule, term rule, and primary rule. So in this class lecture, we have the methods that represent these rules. So the grammar, the combination of all the rules here, defines a syntax of input. In other words, we can apply these rules to the input, and if the input passes every rule that happens to be applied to the structure of this input, and if every rule holds correctly, then we have a good input, and therefore we can generate proper syntax tree for this input. So anything that fails to pass the rules is an error. Arithmetic expression has to pass all the rules before it can be successfully evaluated. So let's take another simple example, 3 plus 2. So how does this example here pass all these rules? So first of all, we encounter token 3. So symbol 3 or token 3 is a term. So in other words, we expect this to be a term. Why is it a term? Because we check it whether it's a primary. And it is a primary because it's a number. So because it's a number, primary is correct, and therefore term returns back here as a correct term. Then we observe that the next symbol is plus. So because we already passed this stage of evaluation, because we already determined that 3 is a term, then we have the plus sign, which happens to be the binary plus operator. And so it's recognized by the expression rule right here. So what we do with this with this definition of the rules is that we essentially apply to everything that's remaining after the plus sign, which is this. We just say that let's check it as we did with the beginning of our expression, and we're just going to go back to the expression and check for the term. And of course, yes, term, primary, and we determine that it is a number. So therefore, this comes back as primary, this term comes back as a good term, which means that expression evaluated well, and this comes back as the internally was understood as the number, and therefore this rule was applied successfully. And the meaning of it is that then, of course, we don't have anything else. So this ends our evaluation, and this should construct very successfully. The syntax tree, very simple idea, with the plus node at the top, and left-hand side and right-hand side with number 3 there and number 2. Both the left-hand side and the right-hand side will represent the operand. So this results in the generation of this tree based on these rules, and the most importantly, this was the result of taking this path right here, because we determined that 3 is a term, so this term became 3. Plus is plus, so plus remained as plus. An expression, we checked again, we found a number, and this expression became 2. So 2 plus 3, and then part of the semantics here is that as we understand terms and primaries and expressions, we begin to construct these nodes as we move through this input. And then we decide that we need to make these links from the plus to its left-hand side and the right-hand side, and so it will be using these links, and this will be the end outcome of parsing this expression that we have initially 3 plus 2. So basically we can find the rule here which satisfies essentially this expression satisfies one of the rules that we can locate in our grammar, and that means a success. On the opposite side, expressions such as 3 minus 5 with the division sign right here does not evaluate to a term because the term requires that the division operator must have 2 operands. Essentially, as we begin our evaluation, we'll just run into the primary, followed by the division, followed by the term. But the term is missing, right? So essentially right here, we don't have a part which is required by our grammar, because as we start moving in this direction and we find primary and we find everything else, but eventually we will fail to find this term because it simply is missing. So this is a quick overview of the grammar rules that actually every rule here is implemented in this class, and you can see that we have this primary rule, we have the term rule, and this expression rule. So we're just going to do a very quick walkthrough through the logic here to make an overview of the implementation of these grammar rules. So this time I'll scroll this back up to make our grammar rules visible, and we'll try to walk through this code and see how it corresponds to what we do with the set of our rules.